First, thank Matthias for organizing this meeting. It's going to be great. I'm really excited, and I'm especially happy to see all the new postdocs in the group. So welcome. Okay, so I'm going to start us off with probably the most formal presentation of the meeting. You'll know it's not phenomenology because I'll largely be in 3 dimensions, and I'm going to try and focus on work that's in progress with Victor and Gonzalo Taroba, but also go through a quick summary of some recent results we had during the past year with Xi and Gonzalo, based on a line of development that's been going on since 2004 or so. So the question is, well, so we all know that accelerated expansion dominates our universe on long scales, both in the late universe and we think very plausibly in the early universe. In field theory, the cosmological term is the most relevant term, and we need to take it seriously. And in string theory, despite recent reports on CNN, the typical behavior is positive potential energy. So almost every term in the effective potential in string theory is positive. We have these interesting sources of negative potential energy that contribute as well, plausibly giving us metastable minima. And that's an ongoing enterprise to understand that as well as we can. Okay, and finally, at the level of what you might call thought experiments, there's this evidence by Gibbons and Hawking, going back to all that beautiful GR stuff in the 70s, suggesting that the area of the cosmological horizon in de Sitter space behaves like an entropy, much like black hole horizon areas do. And exactly what that means demands an interpretation. And more generally, we need to understand quantum gravity in this realistic and generic case of positive potential energy. We won't understand either reality or quantum gravity until we treat that case. Okay, so I'm going to because time is short, I'm going to kind of rush through. So lately what we've been doing is working with a particular framework for holographic duality called DSDS. And we've been getting some more traction on it using tools that have been developed in kind of the formal side of theoretical physics lately, including ideas of quantum information and how that maps to holographic duals, and also this TT bar deformation that I'm going to get to. So in the case of quantum information, there's an interesting idea in play now that space-time comes from, it's kind of knit together by entanglement. There's a kind of prototypical example of this, which is a eternal 2-sided black hole, a spatial slice of which I've drawn here, which is dual to an entangled state of a pair of CFTs. And one of the outputs of our recent investigation is that we find an analogous statement for de Sitter. I'm not going to dwell on this, but we'll show it in passing. So we have a proposal which is grounded on really, I would say, 2+1 independent arguments that I'll review for you, that de Sitter in, say, d+1 dimensions is equivalent to 2 coupled, cut-off, d-dimensional CFTs that are further constrained by a residual gravity. So we don't get rid of all the gravity. We have gravity in the lower d-dimensional theory. And for example, if we focus on 3D to 2D, the gravity is basically a set of constraints. So it's tractable. And this statement, it's sort of concrete. It's not perfectly precise, but it's has content, and it follows, as I say, from 2+1 independent arguments. So the first argument is the following, just a kind of macroscopic way of organizing de Sitter space-time. So here, what I've written is the metric of either ADS or DS in d+1 dimensions. I've written it in parallel in both cases as a warped reduction to lower dimensional de Sitter. So this is a simple statement about the metric macroscopically, with a warp factor, which contains the redshift factor G0, which is either a sine or a sinh, depending on whether you're doing de Sitter or ADS in the bulk. So these two redshift factors agree as you go toward the infrared, toward low values of the G0 factor. And in the Penrose diagrams, the picture is as I've drawn here. So ADS with de Sitter slices cut off at some scale, it has the geometry that I've sketched here in its Penrose diagram. In the de Sitter case, remember that the Penrose diagram is a flat square, but each point, aside from the very edges, is a d-1 sphere, a circle in the case dimensionality I mentioned. And each of these regions is therefore like this region. So it's a de Sitter region, which locally in the infrared looks just like this one. Okay, so at this level, we see this statement of an equivalence, at least at low energies, and then the de Sitter one is cut off and coupled in some way. Okay, so this is a bit of a busy slide, but the next step, the second argument, which is the thing that made me take this quite seriously when we discovered it a bit later with Bart and other people, is to simply follow our nose. So start with ADS-CFT, start from the brain construction that Juan originally introduced to argue for ADS-CFT. That was a bunch of brains at the tip of a cone in general, the base of the cone being positively curved. In the effective theory, what's going on is you have an ADS minimum, which comes about through a balance of negative potential energy from positive curvature played off against positive potential energy from flux. The flux is equivalent to the brains. So the brain construction consists of brains probing something. In this case, in the ADS case, it's a cone over a positive base. Okay, so we know in ADS, in string theory, as I very quickly reviewed before, thanks to the Dine-Seiberg problem, the potential goes to 0 either from above or below as you go toward large radius weak coupling controlled regions. So the simplest way de Sitter can work is such an uplift that I've drawn here. So let's take that into account. The positive curvature is now replaced by something with the opposite term and another additional term with a compensating sign. So whereas we get a cone from this equation of radial evolution, in the de Sitter case, just using this essential feature of the uplift, instead what becomes of the cone is instead this radial evolution, which any cosmologist will recognize as like a closed universe in the radial direction. So rather than this cone that goes off forever, we get a closed universe. We have two places to put the brain sources, which correspond to the flux. And so from this completely separate microscopic argument, where again we just start from ADS-CFT, we add stuff to get de Sitter in the minimal way, and we see what happened, what became of the brain construction, we're led to the same statement. And I want to stress again that at the macroscopic level, this would have, happened regardless of the structure of this metastability. But this argument depends very clearly on the metastability, and that's a feature of, it's kind of like the mother of all swampland ideas, if you like. We don't have a hard cosmological constant. That's something we could write in field theory easily enough. We don't have it in string theory, and that plays a role in this agreement of the two. So the two. So in this picture, they're here. Sorry. Yeah, but yeah. In the brain picture, so we find that so in ADS the cone goes off forever. The flux just goes off to infinity. In the DS picture, it's this radial evolution where it goes. It's a bang crunch in the radial direction, and so there's a sink for the flux here, which is the second CFT. Of course, in all these cases, the brains are traded for flux in the full solution. Okay, so I called it 2 + 1 arguments. The third is this DSC conjecture, which I think has other problems when you try to make it a complete story, but it leads to the same statement, actually. So there, as many of you are familiar, because it's a useful way of organizing cosmological perturbation theory, the proposal there is that a CFT partition function computes the wave function of the universe on a space-like slice. That thing is a functional of the metric, but at this step is just pure field theory on one side and the bulk gravity theory on the other. However, if you then want to compute anything like an expectation value at some time, you have to integrate over the metric and other sources that are arguments of this functional, and integrate O, psi, dagger, psi. So that brings in the two CFTs again. So one Z and another one. So even in this case, we get this same statement. Okay, so to me, this is likely not to be an accident. This statement is still quite ambiguous, of course. We haven't specified exactly how the cutoff works. It's how it interpolates from the infrared toward the different geometry that de Sitter has in the UV. And that's what we're getting closer to nailing down, especially using this TT bar stuff lately. So there are a bunch of old calculations that enter into this, including holographic RG treatments, treatments of the coupling between the two sides, the two warped throats, calculations of the behavior of the quasi-local stress center, which we'll use today. And what's, again, going on lately is some additional elements of the dictionary, first in terms of calculations of entropies and an interpretation of the Gibbons-Hawking entropy, and then the TT bar. So I'm just going to quickly review this first topic, the quantum information stuff in this duality. Because the paper's out, you can read it. I gave some people a heard talk about this at the strings meeting, so I'll just be very brief. Basically, we've seen already that we have a finite cutoff scale in the de Sitter case. We know what scale it is, and we know the corresponding dimension of the Hilbert space of that cutoff system. We also know there are interactions between the systems, and if those are strong enough, you might expect that the lowest lying state would be highly mixed, in which case the density matrix of one of the two sectors, if we trace out the other, you might expect it's approximately just proportional to the identity. In that case, if that's true, an immediate statement is that the Renyi entropies should agree with the von Neumann entropies, and we'll also relate to Gibbons-Hawking shortly. And okay, long story short, that turns out to be true. It's a mercifully easy version of the so-called Ryu-Takenagi calculations to analyze these entropies using the gravity side, and we do that and find that the statements I just conjectured are true, that the Renyi entropies agree with each other at large C and with von Neumann entropy. Okay, so with that combined with the dimension of the Hilbert space I mentioned, we have this large equation of all these things being equal, and it gives a interpretation of Gibbons-Hawking in the following sense. So we have these two sectors. I was describing the density matrix we get from tracing out one in favor of the other. Well, who needs to do that? It's this observer who never sees this stuff, who really needs to trace out the second CFT, or the one over here on the left. And that person has this entropy. So maybe I should have gone a little slower and said that the Ryu-Takenagi surface here is this dot in the middle of the Penrose diagram. It's a sphere. It has a certain area in Planck units, and it's that also agrees with the Renyi entropies. So that surface has this area, and that area is also the horizon area for this observer. And so in this sense, we get a much clearer interpretation of the Gibbons-Hawking entropy. We know who we're tracing out and why. So, sorry.
So this sphere that you draw on the right, is it one spatial section?
It's exactly, it's at tau equals 0. It's this slice of the space-time.
And then the boundaries are the two hemispheres.
The boundaries. So the most UV slice is here, right? So this is the place where that warp factor sine W in my previous equation goes to 1. It goes to the most UV it can go. So is that what you're asking?
I just want to understand what is the position. Should I be able to see the boundary Cauchy slice on this sphere?
The boundary Cauchy slice. So this is a full spatial slice. This is a full spatial slice. You can start your initial value problem, your initial conditions there, and evolve up or down. The future boundaries here. I mean, I guess I'm not sure what you're asking.
Well, I guess I'm asking where is the boundary on the right, and in this picture.
Where is the boundary?
For instance, where is O on this sphere on the right?
Okay. O is like over here. This is not a boundary, but O is here in the middle of this. So this is O's. This blue line is O's horizon. Okay, so O is here on that picture. It's not a boundary though. Okay, so good. So let me go now to the thing I wanted to get to, which is what we're doing these days. Where did it go? Okay, so it's clear from what we said before that this duality involves some kind of irrelevant deformation that flowing from something that's equivalent to a CFT on de Sitter to this different ds-ds bulk geometry. Again, they agree toward the infrared in this purple region I've sketched here. We have two sectors that agree with this low energy ADS-DS picture, but they do something else as you go up to the UV of each of these two warped throats. Okay, so that's, so we've been on the lookout for some traction, some tools to use to understand what kind of irrelevant deformation this might involve and how to control it. And in fact, there's something that's been developed in field theory, which is very interesting in itself, of course, over the years, actually, starting in 2004, paper by Cosmological, and then it's become a thing lately on the archive. I'm not sure about this 12-year time delay, but there's a paper with Smirnov where they basically controlled a kind of simple irrelevant deformation in a way that you can, it doesn't even require, so it's a deformation you can make for any matter theory, integrable or not, and get results for how things like its energy levels are addressed by the deformation. This is not exactly just adding an irrelevant deformation and dealing with the consequences. It's more a step-by-step procedure, a trajectory through the space of quantum fields theories, which is generated by, at each step in this trajectory, one computes the stress energy tensor, formulates what is called T2 bar, but is really the determinant of T, and one evolves a step generated in the flow generated by this TT bar at that step. So as a result of, so what Cosmological showed is that for this theory formulated on flat space, which could be compact, this TT bar operator factorizes. So the expectation values of it in an energy and momentum eigenstate n factorize. So we can write it, so as you can see on the right-hand side, we have the determinant of T, but we've written it as a factorized thing, which is not a priori obvious, but he showed that it's true using the symmetries and cluster decomposition. This is also true just by large C factorization much more generally in that limit. That is to say, we don't really need to fix the space-time to be flat if we work at large C. So we'll do that. Having understood this, one can combine it with the fact that TT bar generates this flow, which we can write in terms of the energy levels. Here, this curly E is, so basically the energy density is curly E over L squared, where L is the size of the space the theory lives on. So on the left-hand side of this relation, we have this deformation by lambda. On the right-hand side, we understand the nature of the stress energy tensor. So the TT component is energy, the spatial component is pressure, and so on. And putting those things together, we get an interesting differential equation for the energy levels as we move along this trajectory. Okay, so here this prime means differentiation with respect to this one dimensionless variable lambda over L squared. And here's the equation that we get. It has a nice solution. And this is the result for the energy levels as we go along this flow. So it's a very powerful statement. Now, three of the people here in our group, Sergey, Victor, and Mehrdad, showed that under these circumstances and some other circumstances involving flat space or ADS space, you get the same results from a certain form of two-dimensional gravity, JT gravity. There's also a version of this that Guika studied with some current JT. So I think Victor wants to write a paper, JT equals JT, but we'll see if that works out. OK, so what we're interested in is a holographic duality. I'm going to circle back around to de Sitter momentarily. But first, I need to share the next step in this TT bar development, which is, people naturally ask the question, what is this doing if we do work at large C? Is there a holographic description? So it's clearly at some sort of irrelevant deformation. It's going to affect the boundary of ADS. And these folks argued that the way it affects the boundary is to just chop off the space at some radial position. And having proposed that, they then compute a lot of things, include with the stress tensor of this dual description being proposed to be the quasi-local stress tensor, the Brown-York stress tensor on this boundary. And when they make this hypothesis, they can then test it with calculations of the kind of thing I just described, the dressing of the energy levels, and you get exactly the same answers. So at the level of pure gravity, it's a very nice result. And we can get a lot of traction by generalizing this to a bulk DS3. So this part of the story is just as easy to analyze if we consider the bulk to be DS3 as it is if we consider the bulk to be ADS3. Also, we're interested in these de Sitter slices, as I explained previously, and even though that has more rich time dependence than the static cylinder, at the neck, the Christoffel symbols vanish. And in fact, we still have some simplifying statements. Things like the stress energy conservation are identical there, and we can form our states there and evolve. So anyway, I won't have time to go through every step, but a lot of this survives if we do bulk DS, and in particular, we can easily compute the energies and how they're dressed with the bulk DS as opposed to the bulk ADS. So this was kind of words. What I'm going to do now is do the two cases in parallel on this slide. So just repeat what these authors did, keeping a parameter eta or a sign eta that could be +1 or -1, plus for ADS, minus for DS, and just see what happens to the differential equation for the energy levels and its solution. OK, so we're going to make the same hypothesis that the duality of the stress tensor is to the quasi-local stress tensor. It has good properties like conservation and so on. Well, the result of this is very simple. The differential equation I wrote before had a 0 on the right-hand side. Our differential equation here has a term that survives, so one extra term in the bulk de Sitter case. And here's what it is. OK, so I just rewrote it again. And what the game now is to figure out what we need to do on the field theory side to generate this term, generate the equation with this extra term, building on the original TT bar deformation. So in these 3 lines, I'm just going to indulge in some answer analysis. So I'm going to do something that will produce this term, and then, well, it's already in front of us. The answer will be a well-defined flow involving another parameter. So we have this curly E, this energy density numerator. It's basically the energy density times L squared. And it could depend on various things. It could depend on time. It can depend on the original ratio lambda over L squared. And what we're going to end up doing is introducing a kind of obvious new parameter, which is the 2-dimensional cosmological constant lambda 2. And so this is another dimensionless ratio on which this thing can depend. OK, so we still have that TT bar is generating d by d lambda, but now there are 2 terms that includes. And the second term, given this new parameter, can generate the new term in the equation that we had on the gravity side if we have an additional equation governing it that I've written here. And solving this and then setting lambda equals 1 over big lambda at each step would produce this term. Now what that means in sort of the original flow in the space of theories expressed in terms of the action is a very natural thing. We flow each step with a TT bar and a lambda 2 that in a coordinated way. So here's another way of writing it, step by step, with the two related to each other at each step. So that is a thing which generates this extra term and hence which knows about the bulk ds as opposed to the bulk ads. Okay, so this is our procedure. At each step, we do this coordinated flow, including TT bar and a relevant deformation. This makes sense also in terms of the warp factor. So as you go from some IR scale, some UV scale down, de Sitter decreases more slowly. So having to add in a relevant perturbation in this trajectory makes sense from that point of view. So the idea here is to, again, to specify a flow in field theory space that generates not the original Magot-Mazet-Verlinde chopped off ADS throat, but which instead generates one of our two warp throats with its different geometry. And we can do that basically in the way that I described with the boundary condition that the two must agree in the limit that we already described. Thank you. Perfect. So they must agree. The ADS, DS, and DS, DS must agree in this regime. If we bring the cutoff all the way down there, they better agree. So that's our boundary condition. Okay, so here's the map of parameters in this duality. For string theorists, this statement is very familiar in ADS3. The thing I want to focus on is this here. So in this ADS version, once again, there's a pretty seemingly successful proposal that this lambda has the effect of chopping off the ADS space, but leaving in just the ADS below that radial scale pristine. So it's like a dead ADS and then cut off. And that kind of corresponds to the fact that lambda was of order 1 over c. So it doesn't really have an effect at leading order on the bulk geometry. Here we have that, but we also have something that is of order c, and the combination can make a difference at leading order at large c. Okay, another thing about DS3 as opposed to ADS3 is that the black holes are kind of trivial. I'm not sure what the full significance of this is, but it's, for example, without spin, just for simplicity, a black hole is simply an identification of our spatial coordinate phi. Each point in this Penrose diagram was a circle, and now it's a circle of smaller period, and that's all there is to a mass at the two poles. So we can, do all this stuff with the quasi-local stress tensor, compute it, and just directly obtain the formula for the dressed energies. It's a little bit of a trick. Now we're working with the field theory on the corresponding tall de Sitter space that corresponds to this excitation. And we're looking at the ground state in the sector with this mass, in the sector with this periodicity. So one thing people who've looked at TT bar might be wondering about is this Dirichlet problem, where you try to cut off the space at some fixed on some fixed radial slice, has a funny feature that, going back to work of Mukund Ranganami et al., that it has some modes that are superluminal. In our case, we do the analogous analysis and we don't find such modes, and it's related to the fact that the black holes are really trivial in this theory. They don't have the usual kind of horizon. So but anyway, it seems like somewhat ironically, the bulk de Sitter case has a nicer property in this regard. Okay, so good. So here's the punchline. We can generalize TT bar in a simple way to obtain the simple generalization of bulk ADS to bulk DS. we're working in the large C approximation where we have this factorization statement on the field theory side immediately. And that matches the bulk gravity sector by construction. So we're giving, it seems, an answer to this question we've had for quite a while, which is, how do I formulate the field theory side to produce the bulk de Sitter? And this TT bar combined, basically the methods of TT bar and the way people have related it to holography already, give us the tools and ideas to do that. And it just seems to require this simple coordinated modification between the irrelevant flow by TT bar or .t and the two-dimensional identity operator on the compact space. So there's a lot to think about here, obviously. A sort of short list is this. What do the boundary conditions at the UV slice really mean? What's going to happen at finite C? Of course, it's at finite C where we start to see very essential features of quantum mechanics, including flux quantization and string theory metastability. What about other sectors? So this Verlinde et al. Thing was limited to the pure gravity sector on the face of it. People have started to talk about higher dimensions, though, for that, and that could help with us with this as well. So are we good? Yeah. Perfect. OK, let me stop there and ask for more questions.